Okay, hello, and welcome to my demonstration of assignment 4. So let's take a look at what was required for this assignment. Oops, get that full screen. Okay, objective is to use the CC1352. And we're going to have the ADC task on AD0, Uart display task, PWM task, and heartbeat function. This is very similar to the previous project on the TIVA C123. So let's take a look at the data sheet. Get this full screen. Okay, so we're going to be doing ADC0, analog to digital converter, on pin 0, which is pin 2. And then we're going to have, we're connecting the Mark II Educational BoosterPack right on top of it, as you can see down here. So if we take a look at the pin for the booster pack, pin 2 is going to be the horizontal joystick. Okay, so we're taking ADC values from the horizontal joystick. Next up, we have the Uart task, Uart display task, so we're using the Uart. Then we have PWM on DIO7, and DIO7 is going to be the green LED on pin 40. Now, it's unfortunate that pin 40 is used for this because pin 40 is going to be also using the buzzer. So that's why the code isn't running right now, because it's going to be very noisy once this code actually starts. Next thing we have is the heartbeat function, just a simple blink on the red LED on DIO6. Let's verify that DIO6 is the red LED. Now, because I've decided to slap the booster pack together, DIO6 is also going to be flashing the backlight for the LCD screen. So that's just an unfortunate coincidence that it's using the same pin. But that's just requirements from this assignment. And right, so the PWM, the heartbeat, and the ADC, that's going to be everything. Let's take a look at the code. So here's the code I developed from the Hello Empty project for the CC1352, which is this one. So I developed the code from this one. Added in some header files, and then here are my global variables. I have one for ADC, I have one for the timer, I have some for the PWM, I also have some for the PWM. The PWM code I used here was actually developed from, on the Resource Explorer, developed from this PWM LED2. Okay, this delay function is not used. Fake blocking is not used. Work task and urgent work task is not used. Stack size is not used. Do urgent work. This is going to be my PWM task. We're basically going to be setting up the PWM. PWM is going to be config PWM 0, which is going to be in this, from this SysConfig file. Over here on the SysConfig file, you can see PWM. We're having that config PWM 0. Looks good. Make sure it sets up correctly. Start it, and then simply update the PWM with the duty cycle, and then go to sleep. Heartbeat function, very simple. Toggle LED 0. LED 0, again, from that sysconfig file, if we go to the GPIO, GPIO LED config GPIO LED 0 is going to be LED red, which is what we agreed upon for this assignment. It's going to be doing that every half a second. Urgent work task function. This is the function that's being used for the task in the TI-RTOS, and it's simply calling that do urgent work function, which is the PWM. I thought about changing this, but I'd have to change it in multiple places to update this. So I just left this do urgent work. Not very helpful function name. Yeah, as a matter of fact, this task sleep never executes because this do urgent work has an infinite loop. So that never executes. Here's my Uart task. This is very similar to the same Uart code that I developed for the TIVA-C123. As a matter of fact, it's the exact same code. The only difference is initialization of the Uart. We're using 115,200 baud rate, and we're using the config Uart 0, which is coming from that SysConfig under the Uart config Uart 0. Decided not to bother using the display driver because the display drivers seem to be having some issues with compatibility with TI-RTOS, or some interruption was causing it to not function properly. So I'm using just the basic Uart here and printing characters to the Uart. This Uart code was also developed from the Uart Echo for the initialization of the Uart. So here is the code that was used on the TIVA-C123. Exact same code pasted in here, including the semaphore wait, semaphore, same semaphore setup as the TIVA-C123. Everything's looking the same. ADC is configured from the SysConfig. We have ADC up here, config ADC 0. That's being initialized. And then again, we have that semaphore wait. This time using ADC convert to get that value into our global variable. Here's the timer task. This is the exact code from the TIVA-C123 code that I developed, but you'll notice that down here on the post switch, when this occurs, it's just taking the ADC value and putting it onto the duty value for the duty cycle of that PWM. So it's the exact same code. This is even the same comment from the TIVA-C123. I just added in this single line of code to enable controlling the PWM using the analog stick, as we'll see in the demonstration. Here's the main. We're going to be initializing PWM timer, Uart, ADC, GPIO, and board. We have the timer. We're setting up the timer here. This is going to be running the timer task, which is up here. This is running every 1 millisecond. Or 1,000 microseconds. Let's just change that comment. Okay. And then this code was developed using the Resource Explorer Timer LED project. This delay function is not used. Okay, let's look at TI-RTOS. You can see if I go back here on the tasks, we have our PWM task. It's called hard work. ADC task is called ADC task, and the Uart task is called the Uart task. We go back. On the idle, we have our heartbeat function. And not using the timer, not using any of these other stuff. On the semaphores, we've declared ADC sem and Uart sem. These are binary semaphores. And that's about it here. I think we're now ready to make sure that this builds. And we're going to run this program. Let's go ahead and build it. Let me make sure I'm still recording. Okay, looking good. Hopefully that preview wasn't blocking any of the stuff I was looking at. Make this a little bit. Well, I guess I can make it bigger. Well, yeah, I'll make it smaller for now. I'll go ahead and cue the debugger to start as soon as this finishes. Okay, so it built, and now we're debugging. I'll go ahead and connect the COM port. Okay, we're going to also clear the COM port. And then what I'm going to do is, let's make this one a little bit larger. Zoom in on the COM port. Yep. And then we can make the preview a little bit bigger. Okay. And then I will go ahead and start. And then you can see that when I lower the analog stick horizontal, the value goes down. And when it goes up, the value goes up. And then down here, the green LED is bright, and then it goes off. And then it goes in between as I move the analog stick. You can see the heartbeat function is going, and we have the UART with the ADC. Okay, so the next thing we can look at is actually, I'm just gonna barely hear myself think with that buzzer going. Maybe I have to hold this right. Okay, that sounds a little bit quieter. We're just gonna put this back to full screen. Okay. And then we can actually look at this with the logic analyzer. So we're gonna just record for 3 seconds. The red channel is going to the red LED, green channel is going to that green LED, and the blue channel is going straight to the ADC pen. So let's take a look at what we get. What's going on with that sample rate? Oh, I guess it got set to a very high sample rate. Okay, let's go. What? What sample rate do you want? What's the problem here? Okay, we're back. We're gonna try this again. I'm gonna run this one more time. Okay, so now I'm gonna go ahead and turn off the buzzer, and we can take a look at what the waveform has been captured. You can see up here the heartbeat function. It's executing every half a second. toggling every half a second, giving a period of 1 second. Okay, down here, this is the Adc Pen. You can see the voltage going up to a maximum of 3.3 volts, and then coming back down to a minimum of almost 0 volts. You'll notice that when I zoom in here on the lowest, you can see the green LED, the duty cycle is almost completely gone. We have a little spike with mostly 0. If I zoom back out, if I pick the max value, you'll notice that it's mostly on with a little trough where it's off. If I pick a value in between, maybe here, you can see that, you know, we're starting to increase. You could even see here, you know, these the width is 1.941 milliseconds. Over here, the width is 2.447 milliseconds. So the width is increasing on this duty cycle for the pulse width modulation. So, okay, this concludes my demonstration of assignment 4 using the CC1352R TI-RTOS. And yeah, thank you for watching.